So you're live whenever you're ready.
Okay, good morning. So today, the IQUIZ seminar, I'm happy to introduce the speaker, Alexandra Kolla from UT Santa Cruz. She got a PhD in Berkeley, then spent some time here, right? And then in Boulder, but then for good reasons went to UC Santa Cruz because as I just learned, she's also has been an Olympic surfer. So pretty impressive. But she's going to talk about something totally different, local Hamiltonians and quantum cuts. So with that, please.
Thank you for inviting me. Yeah, it's strange being back here after all these years. I don't think I've visited since. A lot of things have changed and a lot of things haven't. Right, so today I'm not going to talk about surfing, which is what I usually talk about. So it's a nice break. I'm going to talk about some work, recent work that me and my student group at UC Santa Cruz are looking at. And I want to get an idea on like the background. So how many people here are in like physics side of quantum computing? How many are in the CS side of quantum computing? And how many know nothing about quantum computing? Or rather, where are the rest? You know, what's like, what did I miss, I guess, is the question. Okay, I don't know, so half physics and half CS. Sounds like my undergrad class. Let's go. Some outliers, I forgot math. I'm so sorry. Math is like all I do. So I don't know why I even forgot it because I'm not in physics or technically I'm in CS, but okay. As a disclaimer, I haven't given a talk in a very long time, pretty much since I moved to Santa Cruz, because I don't like to travel away from Santa Cruz anymore. So I actually don't go anywhere. So that was like a nice opportunity to brush up my skills on giving lectures. But it's my first time in a while, so I apologize if like it's not as polished as my normal talks would be. All right, so today's talk is about local Hamiltonians and quantum cuts. And that sounds probably more intense than what it actually is. But for the computer science, okay, so here's the outline of the talk, and here's generally what I'm going to talk about. This talks about quantum, what we call constraint satisfaction problems, that those of you in physics would probably know as local Hamiltonian problems, finding ground states of Hamiltonians, like, or the Heisenberg model in particular. It's a case of such a Hamiltonian we're going to look at. And we're not only going to look at qubits, but we're going to look at other particles that achieve not just two, but any number of d states, qudits. So I'm going to start with some motivation from computer science, because I am not a physicist and know nothing about physics, about why this work is something that I'm interested in. From classical constraint satisfaction problems, and in particular, two of those that are very prominent in computer science, the max cut and the max d cut, and see how those are generalized directly in the quantum setting and why those things are related via what we call local Hamiltonians, which will bring us to define quantum max cut and quantum max d cut. Very naturally as a generalization. For those of you in physics, you will see that those are exactly the Heisenberg models of Hamiltonians, and talk about some of our preliminary results. That's a paper that appeared at QIP with my students and I, and some what I want to mostly talk about in case you have some cool future directions, because these are very new kind of areas of study in this point of view of computer science. All right, so for those of you in computer science, this is not news. You must have heard of a problem called the max cut. This is just given an input graph. I want to partition the graph with my objective being to maximize the number of edges cut. In this particular case, the graph happens to be what we call bipartite, meaning there are two partitions, the green and the blue, that have no edges within them. So no edges from green to green and no edges from blue to blue. And the max cut in this particular case cuts all the edges, because you can put these two partitions on different sides, and all the edges cross the cut. So max cut is one of the, I don't want to say elementary, original NP-hard problems, which means there is no realistic hope to find efficient algorithms for that. So the next best thing we can hope for is approximating max cut. And there's like a random cut trivially approximates max cut with a factor of a half approximation. So if I randomly put vertices with probability a half on the left or the right, the expected value of this cut will be a half, and you can make this into an algorithm. So a factor of 2, in other words, approximation, depending how you take the ratios, is trivial. And then there's a much more complicated result by Gemmons and Williamson in the 90s that achieves a 0.878 approximation of max cut. And in fact, if a big complexity theory assumption, what we call Unigame's conjecture, is true, this 0.878 is the best approximation algorithm we can hope to achieve for max cut in polynomial time. So max cut is pretty much done in some sense. Morally speaking, we cannot hope for better algorithms, so let's give up. We already have the best. All right, so this is an example of a constraint satisfaction problem where you can see constraints being between two vertices, and you can see this as coloring or assigning 0 or 1 to each vertex, so assigning a value to each vertex such that the number of vertices that achieve different values is maximized, that are connected by an edge. So you can see each edge being a constraint between the two endpoints, and the constraint would be that they need to be different, of different value, 0 and 1. So in the quantum world, constraint satisfaction problems naturally generalize as what we call K-local Hamiltonian problems. And what is the Hamiltonian problem? We're given an exponentially large in the number of qubits n. So if you have n qubits, it's 2 to the n size matrix, a Hermitian matrix. This is known as a local Hamiltonian. And it has a succinct description in terms of local quantum clauses. We'll see exactly what that means in a second. So in any case, you're given this huge matrix, and your goal is to estimate what we call the ground state energy of this matrix, which corresponds to computing, depending if you're minimizing or maximizing. In physics, it's usually minimizing, corresponding to computing the minimum eigenvalue and the corresponding ground state, which is the minimum, the eigenvector corresponding to the minimum eigenvalue. So here is how it looks like. And do I have a laser pointer, bro? No. It doesn't matter. So here's how it looks like. A K-local Hamiltonian is a matrix H, which is the sum of terms. And this H acts on all the n qubits in general. However, these terms H sub S act on K qubits. So the sub S denotes a subset of qubits of size K, that its H sub S is a matrix only affecting those qubits tensored with the identity everywhere else. So it's succinct to describe if K is constant, for example, because you could give the list of those matrices that are only 2 by 2 or 4 by 4 if it's 2. So this is how, let's say we have 4 qubits, that would be 2 local Hamiltonian. That's, the dots like quantum gates. It doesn't matter which gate it is, but I only denote the fact that every time only 2 qubits are passed through this gate and something happens, and everything else is tensored with the identity, so the other ones remain the same at every point of this interaction, and then you sum up over all these terms. So this is a 2 local Hamiltonian example. So this is what I said. And why is this a direct generalization of the constraint satisfaction problems we just looked at? It is, I swear I had H sub S as a subscript, but maybe I didn't save it in the last edit. So this is H sub S, not HS. It's a direct generalization because if it happens so that our H sub S matrices are just diagonal, just, completely diagonal matrices. Then this is exactly corresponding to classical CSPs, because for diagonal matrices, any, in fact, but in particular, the minimum eigenvector of such matrices would be a basis vector, which corresponds to a classical solution. And you can map a classical CSP to a Hamiltonian problem one-to-one like this, like it's a bijection. All right, so I don't think I need to motivate this problem much for physicists, but it's a very important problem to physics because it's the problem of estimating the energy of a quantum many-body system when cooled to near absolute zero, what's like the lowest energy state. So these things have been studied way before modern computer science came about and started being interested even in CSPs, let alone quantum CSPs. But not only that, it is important to complexity theory from my point of view, because as I disclaimed, I'm not a physicist and know nothing about physics, other than what I learned from quantum computing. It's the first known QMA complete problem. And if you don't know what QMA is, you will still not know at the end of this talk, but it does not really matter. You think of it as the quantum analog of NP. So QMA is for quantum complexity. What is NP for classical complexity? So it's basically hard. That's all you need to know. So this is actually the two local Hamiltonian problem is the first problem that was shown to be QMA-hard. I think it was by, okay. Sorry, I did not put the reference there and I completely blanking out on the name. I will remember it by the end of this talk. And not only that, if you happen to be in this subset field that cares about quantum Hamiltonian complexity, it's a central problem. In fact, the toy problem, I don't want to call it toy because it sounds easy. It's a very hard toy problem in the quantum Hamiltonian complexity realm. And it uses a lot of tools from complexity theory to uncover limits and structure of physical systems in nature. So it nicely combines classical and quantum, which is kind of like what I like to do. Sorry, my hair keeps getting tangled in this body and it's distracting. All right, so why is this problem hard to begin with? Let's give I'm not going to give you clearly the proof that it's QMA-hard because this is not what we're talking about. But why would we expect it to be not easy? There are a few reasons. Even though computing eigenvectors and eigenvalues is not hard, the reason here, or the difference here, is that we're given an exponentially large matrix. So we can compute the eigenvalues and eigenvectors, but the algorithms we know of how to do that will necessarily take exponential time, which is linear or quadratic, I guess, in the size of the input, still exponential for us. Remember, our Hamiltonian has a succinct description because we can give these local terms, but because the terms don't commute unless they are diagonal or have some special property, we can only ask about computing eigenvalues of an exponentially big matrix, and we have no way of doing that as of now. So the other reason why this is expected to be a hard problem that I don't think I have in here is that it's a direct generalization of classically hard problems like max-cut. So of course we cannot expect to solve it easily because it embeds problems that we know it's NP-hard already. However, what does it mean? Okay, so for max-cut, remember it was hard to solve, okay, but then we had these elaborate approximation algorithms that in fact they were proven to be tight, assuming some complexity theory conjectures. What does it mean to even approximate an exponentially large vector? Because describing this vector would take exponentially large space. In any case, you cannot just give an output that's an exponentially large vector in polynomial time in general. This is not possible. So classical algorithms for approximating energy states, ground states of Hamiltonians have been around for a while, but they need to have a reasonable, succinct representation of the class of quantum states that approximate the ground state. And this is called an ansatz. So the simplest such class of quantum states is n qubit product states. This we can represent efficiently because for each qubit, we need to give one state. And this is the quantum analog of product distribution. And it's just given by one qubit state tensored for all the qubits. And already, even though product states are not entangled, they generalize in particular basis states that happen to be product states. And we already said basis states are solutions to classical CSPs that are already NP-hard to approximate. So even approximating the best product state that we have hoped to, we describe it in polynomial time as output, is not clear how to do it algorithmically. And in fact, it's hard to do it. All right, so this is the general setup and motivation of the problems or problem, I guess, we're going to be looking at. And the particular thing we're going to focus on from the class of local Hamiltonians is the quantum Heisenberg model that has been fundamental to study magnetism. And it's just a direct generalization, as we will see, of the classical maximum cut problem that I just described. This is a two local Hamiltonian problem. And we have constraints at Hij indexed by two qubits I and j. So when I say Hij, it means it acts on qubits I and j. This picture that I had with the gate that passed through the two qubits would be Hij. And this is a local term. Don't be afraid. This is going to be easier to understand in a second, of how a local term in this two local Hamiltonian looks like. Its identity minus alpha, beta, and gamma are just constants, and we will see what we care about. And xi's, etc., are the Pauli matrices x, y, and z that I will also define, but you probably already know. And just I denotes that it's a 2x2 matrix applied on qubit I. So the Ij term has tensor product between Pauli matrices that act on qubit I, tensor qubit j, identity everywhere else. Okay, so is it clear how the format? All right, so there are three important cases that have been extensively studied in the literature for this problem. One, where alpha, beta is 0 and gamma is 1. And this is exactly the max cut problem. So let's go through this exercise in a second and see why this is the max cut problem, so we understand what's happening in terms of more mathy, getting our hearts dirty kind of thing. The second one, which I'm not going to talk about because it's just similar to the third one, is what we call antiferromagnetic XY model, where only the Pauli's X and Y survive, gamma is 0. And the third one, which is the antiferromagnetic Heisenberg model, the more general case, is all of them are 1, which is actually the quantum max cut, the one that we're going to be studying today. So one thing I want to notice as a motivation is that for max cut, we already saw, if a graph is bipartite, the example I had before, it's very easy to cut it so that it's very easy to find the max cut. Because it's in polynomial time, I can find the bipartition. There are many algorithms to do that, spectral or combinatorial. I can find the bipartition, and I know this is the best cut. It cuts all the edges. So max cut on bipartite graphs is absolutely trivial. There's a linear time algorithm to do it. However, for quantum max cut, even on bipartite graphs, is notoriously difficult. So there's already like a big difference. The only solutions for antiferromagnet is on the 1D chain on the complete graph, which actually we're going to come back to the complete graph at the end of this talk. It's important that we know how to do that. The reason that we do is that the matrices that we get end up commuting. So it's easy to, or it's easy to figure out what the end matrix is anyway. So clearly both of those models, I mean, not clearly, but you would expect by now, both of those models are QMA-hard to solve exactly. So we're dealing with approximating them. But before I present approximation algorithms for those things, let me quickly go through the exercise as to why, if alpha and beta are 0 in the Heisenberg model, we get exactly the max cut. Remember, Z is the diagonal Pauli matrix that has eigenvalues 1 and -1. And the eigenvector ket 0 is the the 1 for the eigenvector ket 0 and the -1 for the eigenvector ket 1 basis states. Thus, Z tensor Z diagonalizes in the same basis. And the eigenvalues you can easily compute of the I minus Z tensor Z is 0 and 2, corresponding to the two basis vectors. So this is the situation. So what does it mean if each local term diagonalizes in the same basis? It means the whole matrix diagonalizes in the same basis. So you know exactly what all the eigenvalues and eigenvectors are of this matrix. And in fact, if neighboring qubits are set to opposing standard basis, so one is 0, the other 1, or the one is 1 and the other is 0, meaning there's ket 0, 1 or ket 1, 0, then the contribution to the whole thing is 2, which means a contribution of an edge being cut is 2. And if they're 0, 0 or 1, 1, so same, the contribution is 0. So since they're diagonal in the same basis, the largest eigenvalue is just twice the maximum cut, because every time I set qubits connected by an edge to 0, 1 or 1, 0, you get a contribution of 2. So literally this minimum eigenvalue, or actually, sorry, maximum, because minimum would be only with the z's, maximum we use identity minus the z's to switch the problem from minimization to maximization, but it's not important because the diagonalization, identity is, diagonal matrix, so it doesn't make an actual difference. So we switch to maximization implicitly here by doing identity minus z times z. In any case, for this matrix, every edge cut contributes 2, and every edge uncut contributes 0. So the ground state, which now for us is the maximum eigenvalue and eigenvector, would correspond exactly to a maximum cut, which is already NP-hard to compute. Right. So this is why kind of like this problem is encompassing, max cut, and also why it's expected to be harder than max cut in its general form. So one thing to mention, because it'll generalize shortly, is that I could just write down this Hamiltonian, its local term, as a sum of projectors, because this is what this is. You project onto the 0, 1 and 1, 0 space spanned by these rank 1 matrices. All right, so now the general case, which is also called the quantum max cut. Now it's kind of like a little more obvious why this generalizes. Why do we even call it quantum max cut in computer science? X, Y, and Z are, again, the Pauli matrices, which form a basis with the identity. And these are what they are. So in the quantum realm, in the cut, we just wanted two assignments of the edge being different, either 0, 1 or 1, 0. So this was our payoff function. It counted how many edges have different assignments on their endpoints. And the notion of these assignments being different is replaced by the energy of two local subsystems of qubits onto the projector on the antisymmetric space, which for two qubits is given by the projector onto this Bell state, I guess, the single state, which is the entangled state that I've written there. So instead of having this requirement to either be 0, 1 or 1, 0, we're counting contribution to the projection on what we call the singlet state. So before in max cut, I want to make this very clear because I'm going to use it. We had the projector onto the two basis states that are different. Now in the generalization, you can easily do the math and calculate that these are equal things. The contribution of our solution is how much projection does it have into this operator, which is the outer product of y minus with y minus. All right, so what is known for this problem in the literature already? And these are all very recent results in the last, I want to say very recent, but it's already been like maybe 5 years. That's recent for science, I guess. There's what we call semi-definite programming-based algorithm by Briette and D'Oliveira Fido and Valentin, that give approximation of 0.956 to the optimal product state solution. So the first algorithm of this kind of like line of work, all the algorithms we're going to talk about today are classical algorithms to approximate these exponentially large ground states of the quantum max-cut problem. So there was this STP-based algorithm that approximated the best product state solution. Remember, we already said product state solutions are hard because you already have to solve max-cut. So solving it exactly you don't expect to do, but you can get the 0.956 approximation to the optimal product state solution. Which may not be the optimal solution. There's a more recent work of Garibian and Parek that gives again, STP algorithm, a slightly more complicated STP. The first STP is more like an extension of the max-cut STP, the Gemons-Williamson. It's like projectors onto, in any case, if you know what that is, it's just a generalization of Gemons-Williamson. There's like a subsequent work that uses more complicated STP, Lasserre hierarchies, or what we call non-commutative sum of squares STPs, that gives a 0.498 to the best, generally, to the actual best, possibly entangled, most likely entangled state. And this is the state of the art that we know. And as you will see, we're still like, the approximation guarantees are not that great. So in the hardness side, we know that it's QMA-hard to compute exactly. And there are a bunch of results by a recent paper by Huang, Niemann, Parek, Thompson, and Wright that prove an integrality gap of 0.498 for the basic STP, which matches the previous rounding algorithm. An integrality gap just basically means this method cannot give you anything better. You need to come up with better methods. And basically, this shows that the basic STP that they use does not achieve the optimal approximation ratio. Another result brings unigames, the conjecture that shows max-cut is hard to approximate better than what we know, is brought into quantum max-cut as well. And it says it's unigames hard to compute the 0.956 approximation. And this, if you remember, matches the product state approximation of the first algorithm. What? No, this is a general, for general graph. Complete graph is easy, we know how to do. All right, so this is basically what's known for this problem. I hope I didn't miss anything, but I think that's like the whole picture of what's known. There is another interesting case that you might come across if you go back and want to study this problem further. That's given by the projector under the first belt state, and it's called the EPR. And there's no hardness for that, so this is wide open. There are some things that are there for completeness in the slides. But the one thing I want to go back to, that's why I'm mentioning EPR, is that for bipartite graphs, this problem that's seemingly easier because there is no QMA hardness for EPR. The Z is not there for EPR. Sorry, no, the Z is there, but it's like with a plus, there's a 2 pluses and 1 minus. So this problem that's seemingly easier, it happens to be equivalent to the general quantum max-cut on bipartite graphs. And solving this quantum max-cut on bipartite graphs would already be a big, or answering a big open question in the Heisenberg model enthusiasts group. So it's enough to show it in the seemingly easy problem of EPR. So yeah, there's a reason why you can rotate one side and so on and so forth, but there is no need to get into that.
So a bipartite graph, a Heisenberg model is essentially sign coupled free. So one to do quantum running parallel. Why does that not work? Is it that you don't know the next
Sorry, can you speak a little louder? I have an ear infection and my one ear is deaf.
On a bipartite graph, I think this is sign problem free.
Yeah.
And so one could do quantum running parallel on it and presumably get an exact answer.
But it doesn't, yeah. I mean, I don't know the quantum. I know that there is no algorithm for it, that achieves the optimum for bipartite graphs. That's for sure. But I can't answer why specific algorithms from quantum don't work, because yeah. All right, so this is what is happening so far. And as you may have noticed, I've only talked about other people's work. And I could leave right now and we'll be happy because we probably learned something cool, I hope. Like, I think those are cool problems. But I feel like compelled to mention something about my work since I am giving the talk. So let me do that. So what we did is that we generalized the two local Hamiltonian problem to qudits. You know, think of D as 3. So these are like 0, 1, and 2 value bits, quantum bits, no bits, whatever, dits, treats, I don't know how they're called. That some physical systems actually, you know, are more better modeling things that don't only take 2 states. So this is our attempt to generalize all these concepts in qudits. We need to define the appropriate model, design algorithms that have non-trivial guarantees, and maybe matching hardness for these approximation algorithms. So before we go to that, let me give you the similar to what we did with MaxCat and quantum MaxCat. Let's see why is this generalization to qudits, because it seems kind of arbitrary if I just say, okay, what about qudits? Why does this make sense? And why is this an interesting problem to study? Well, let's go back classically. And now assume I didn't ask you to cut the graph in 2 pieces to maximize the edges cut, but assume I wanted to cut the graph in partition into these sets of vertices that maximize the number of edges cut. So here I have 3, and there's red, green, and blue. So the blue vertices is one set, green another, and red another. There happen to be 1 vertex in the red and green set, but that's fine. And this partition maximizes the number of edges that cross partitions in this specific example of the double star graph, which is called. So similarly to MaxCat, you can ask classically what is known. A simple randomized algorithm, just like for MaxCat, gives a 1 minus 1 over D. You assign randomly vertices to, we can see it as colors or sides of the partition. It's equivalent. And there's a better algorithm that extends Giemans-Williamson to a log D over D squared. And there's other approaches similar that have achieved similar guarantees, but not much else. So now let's go back to rephrasing this in terms of matrices and projectors. So as a 2 local Hamiltonian, the classical max D cat, just like MaxCat, is a projector onto these basis states, these base matrices, that are just a sum of everything being different. So before it was 0, 1, or 1, 0, now it's like 0, 1, 0, 2, 1, 2, whatever, how many colors you have, as long as the colors are different. So it's a projector onto these sums of the rank 1 matrices classically. So this is max D cat. You can write it with a Hamiltonian that each local term is 2 local. Still 2 vertices are only involved, 2 qubits. You can write it down as a sum of those terms, tensor identity. So what we did is generalize, and this is the first, actually there's 1 hardness result, but it's the first time anyone looked at algorithms for the quantum max D cat. And what we did is we just did the natural generalization of max D cat, known as quantum max D cat, where you replace the D colors with D-dimensional qudits now, and the payoff function, which counted the number of edges being cut, with a projector onto this anti-symmetric subspace of 2 D-dimensional qudits, which is rank D choose 2. So it just, the projector onto these entangled vectors that are entangled between the 2 different values of A and B. Like what I written down there, it's easier to see than me talking about what this projector is. So you can now define the local term, the 2 local term of the IJ Hamiltonian to just be the sum of those projectors. So this is our edge interaction, the Hij terms inside the big H matrix. There's an equivalent way to write this, which looks like this. And I'll explain what this is in a second. But why is this way useful? First of all, it reminds us of the two ways that we wrote Max cut, one via projectors and the other via matrix bases, the Pauli matrices that form a basis for the matrices. And here we're doing something similar. You can also a bit, not so easily, but also slightly easily verify that those two things are equivalent. This is called the SUD Heisenberg model in physics. And what are those lambdas? They're what we call the generalized Glenn-Mann matrices. If you know what that is, you may know if you're from physics. There's some higher dimensional extensions of the Pauli matrices and the Gell-Mann matrices, and they form an orthogonal basis for D by D Hermitian traceless matrices. So just like the Paulis, you have some generalization. We have a lot more difficulties than dealing with the Paulis that we're gonna talk about in a second. But this expression is useful if we want to create algorithms that use semi-definite convex programs, because we can write it as inequalities of matrices, as we will see. So, any questions so far on this?
I think it's very fun instead of X interact, Y X. So, summation lambda A lambda B.
Yeah, I haven't studied this model, and I don't know much about it because it doesn't generalize the classical. So I mean, I'm from computer science, so I'm looking at things that are direct extension of like classical things that we care about. It might be interesting in physics, but I have like the vague impression, which I need to check, that if you do X and Y, it might be easier than just doing X and X. Yeah, I've seen it somewhere, I'm sure, but yeah, it's not that I know of that it generalizes any CSP concept because of the nature of like IJ is connected by a one constraint, so you need to apply the same thing. But it's possible, yeah, it's something to think about. All right, so there are a few ways to write. So what we want to find, again, we're in maximization world because we subtracted our thing from the identity in some way. So instead of minimizing, we're maximizing equivalently. So we want to find the maximum eigenvalue of this Hamiltonian that consists of the sum of these projections or the sum of these terms H. Tensor the identity. And you can see this as an eigenvalue problem or as maximizing over density matrices of a trace. It's equivalent. So you can either find a vector solution, which is a state, ground state that maximizes, or the trace matrix that corresponds to it. And that's what rho squared equals rho represents. That means rho belongs to the density matrices of the right dimension. So equivalently, we can write these problems like this. So what we have done is a non-commutative sum of squares semi-definite programming based randomized approximation algorithm for the quantum max DCAT that finds a product state solution. Remember, product states is one example of an ansatz that you could present from an algorithm of mixed states with bounded purity. And our guarantees are as follows. AD is the approximation ratio for the optimum. And it satisfies 1, 2, 3, and 4, bigger than a half, 1 minus 1 over D. This will give us, as we will see, that's better than random, because, and by random, I mean the fully mixed state. So it performs better than random, and then it has some other guarantees. And moreover, these constants match the algorithmic gap for qudits, where D is bigger than or equal to 3, so not qubits. And that means that this particular method, the analysis is tight, so we need different original algorithm, different STP or different other algorithm to get anything better. So our algorithm is tight. And now for the next few minutes, what I'm saying may not make even sense. For those of you that are comfortable with STPs and hierarchies, maybe it makes some sense. I just wanted to flash it out there to give you a general idea of how the STP looks like. It looks like this. We're maximizing the strength function, and we're just, since we cannot maximize over actual all density matrices, then we would have solved the problem. We're imposing constraints on rho that are called imposing that it's a pseudo density matrix. So it satisfies some of the things that the density matrices satisfy, but you cannot clearly, in polynomial time, impose all the constraints that would enforce rho to be a density matrix. So this STP outputs a solution, which is a density matrix or a vector. You can see it as you wish. This vector satisfies some properties that density matrices satisfy, but not all of them. So it's not really a density matrix, it's something else, but it's nonetheless a vector. And the question becomes, like it is with semi-definite programming, how do we take this output vector or density matrix and find something meaningful that connects back to an actual density matrix for the problem? And this is where the rounding comes about, and our rounding outputs something, if U is the vector that the STP outputs in the vector sense, we choose a random matrix and we output a vector that depends on U in some way. So I don't want to spend there's not enough time for me to explain in detail what this algorithm does or what an STP is or what an STP hierarchy is if you're not familiar with this. I just wanted to give you a general idea. But I want to say two things about these results. First of all, explain why they're non-trivial. And second of all, talk a little bit about some difficulties as opposed to qubits that qudits face, which is the interesting part of this. So the first thing is the energy achieved by the maximally mixed state is no worse than half 1 minus 1 over d times the optimal. So the theorem says that at least the algorithm does better than what could be a random assignment. And by random, I mean just the fully mixed state. And yeah, so this is a very common metric to judge the first algorithm for a problem against. At least it needs to do better than random. Otherwise, we're not doing anything. And in fact, when d equals 2, this algorithm, it boils down to the Garbian-Parek optimal algorithm that we mentioned. So you can also see it as an extension of that. What are the basically main challenges that we faced in trying to extend these results to qudits, which I think is the interesting part. So the one challenge was to find this generalization of Pauli matrices that makes sense to define the problem. And those matrices are not as useful as Pauli's or as easy to study. In particular, they're not unitary, which makes STP difficult. And arguing that STP vectors are unit vectors, which is what we want to get qubits or states or density matrices, is not as trivial as just observing that Pauli squared is identity, which requires Pauli to be a unitary. The other challenge that we faced is that the notion of block sphere does not exist for qudits. Only for d equals 2 for qubits. Every state corresponds to a vector 1 by 1 bijectively, or what we call the block sphere. So what you do from the STP is you get an output that it belongs to the block sphere because of the unitarity, and you translate it back to a quantum state, basically. But that we cannot do for qudits because there is no bijection between vectors and actual things that correspond to density matrices or qubits. So this is kind of like one of the main challenges and that we face, which is what I mentioned before. And this is kind of like the picture of how we resolved it, which I'm going to explain in the next slide. So basically, we bound this convex set that we care about between two spheres. what we call the outer sphere and the inner sphere. And in the inner sphere, in fact, we can represent each vector with a quantum state. So here's how this looks like. Oh, I should have done 1, 2, 3, 4, 5. But anyway, so if we say our whole, let's call omega d is a convex set of block vectors for qudits. And while clearly every valid density matrix, every state is a unique block vector, is not the case that every vector gives a density matrix, which is our problem, because our STP just gives a vector. We don't know how this corresponds to states, or if it corresponds to states, or whatever. So we define the outer sphere, which is a minimal ball that contains this convex set. And the pure states lie on the surface of this ball, and the mixed states lie inside this ball. Within this, there is a small maximal ball of radius that consists entirely of block vectors that do correspond to density matrices. So that's what we use. And that's why we're scaling by these factors in the rounding algorithm, so that we end up with a vector, applying a random projection into it, applying a random Gaussian into it, and scaling by the right thing. We get a vector in this inner sphere, roughly, that does correspond to a density matrix. And this is what we round to. And it happens so that it has some guarantees with the actual solution that we can show by using the STP. So the lucky part is that for qubits, the inner sphere and outer sphere are the same. And that's why in qubits, once you get a vector, you have a state. But for us, they're not. So things become challenging. All right, so in the 5 minutes that I have left, I want to talk about something that I would like to study in the future. There is a result by Brandau-Hart that uses quantum definiti theorems. If you know what that is, it doesn't matter if you don't. That show for dense graphs, the optimal entangled state is very close to a product state. Very close in value. So the states may be different, but the values that you get for lambda max or lambda min, whatever you're looking at, are very similar within an additive factor that is scaling 1 over the degree. And if the graph is dense, the degree is like 1 over n. So the factor is 1 over n. So they're actually really close. So the value might be constant. So you have like a 4th to 1 graph. So for the mixed state, then maybe a 4th plus or minus 1 over n. And I use a 4th because that's for the complete graph. Plus or minus 1 over n for the product state. So they're really very close. So dense graphs are not the hardest cases in this situation, because you can approximate at least everything, the best solution with the best product state solution. So what about sparse graphs? Which instances are hard? Similar questions can be asked to classical CSPs. What instances are hard? For example, for unique games, we don't even know what instance. I mean, we know something. And answering this question to the positive or negative would verify or nullify what we call the quantum PCP theorem, which is a hardness of approximation for quantum CSPs, basically. So it's an important question to ask what sparse graphs are hard, or what happens, are they close to product states, are they not close to product states? And the sparse graphs I do care about is what we call expanders. Expanders are graphs that no matter where you cut them, the number of edges crossing the cut is fairly large. So there are no sparse cuts. And they look, they don't look exactly like this, but every cut is X basically. And they have some spectral property that you can argue. The adjacency or Laplacian spectrum lambda 2 is related to the cut value. In fact, all the eigenvalues are fairly large or small, depending if you look at adjacency or Laplace for expanders. So the question I'm really interested in, I think it's a pretty cool connection between classical and quantum, is can you argue that, okay, we know exactly what happens for the complete graph. We can compute it exactly. I said the value is 1/4, we know the state. And we know both the best product state and the best entangled state. All right, so we know that. We also know that expanders, not only do they not have sparse cuts, but is what we call sparsifiers of the complete graph. Meaning, instead of giving you a very dense graph like the complete graph, I can give you a more sparser graph to represent it, where the behavior across every cut is similar as long as you scale them appropriately. So it's a proxy for the expander is a proxy for the complete graph if you have less storage space, for example. So it's something that computer scientists care about. So my main question is, what happens for sparsifiers of dense graphs? We know that algebraically and classically, every algebraic property of those two graphs, cuts, eigenvalues, quadratic forms, are the same. Can we say that about Hamiltonian eigenvalues and eigenvectors? And the difficulty is because these Hamiltonians no longer commute, right? So in classical setting, things commute and things are nice. But when you add the Paulis and all of that, they don't commute anymore. So it's not straightforward to say, okay, if the complete graph has this behavior, then the expander graph would have a similar behavior, depending on the quality of the approximation of the two graphs to each other. So this is a question I'm interested in answering. What happens if we sparsify dense graphs? Are those hard cases? Because expanders are typically hard cases or easy cases for problems. They're kind of like not unknown usually. So depending what problem. And there's some other problems like, what are the hard cases if not expanders? Is there quantum PCP? What about better approximation algorithms? And what about matching hardness? And I'm right on time.
Hey, questions?
Thanks. Thanks for the nice talk. In the limit of large D, so the qudit getting very large D, does this reduce to something classical, and is something known in that case?
Large D?
Yeah, so very, very large local dimension.
No matter how large it is the K cut, the D cut. So the classical analog for all, like you can have an N cut and it would partition, it would put every vertex in its own bracket, in its own set. So that scales with D. All of what's said has nothing to do with how small or large D is, as long as it's bigger than 2.
But there's nothing known in sort of the D going to infinite limit that looks very classical.
I would assume the problem becomes easy. For classical, for sure, it becomes easy because if D is N, then you know exactly the solution. You put every vertex in its own component and you cut all the edges. Quantumly speaking, I haven't actually thought about it, but I would assume it's easy for large D.
Okay, thanks.
Other question? Oh, the other side. No problem.
So, have you looked at this BH result for non-commutative graphs? Whether
Sorry,
for,
can you speak a little louder?
have you looked at the BH result, the Haro-Brandao result for non-commutative graphs? Whether then you still know that the optimizers are almost separable?
The pH, sorry.
The Brandao-Haro result.
Yeah, the Brandao.
Which you had on your last
Okay.
BH.
Now I'm in the same page.
Sorry, Brandao-Haro, whether, that's very remarkable that the
Yeah.
states- So there are kind of slight generalizations, these non-commutative graphs where you could have the same thing. That the corresponding eigenvectors are almost pure.
Sorry, can you? I'm really deaf from one ear, so you really need to speak very loud. I'm so sorry.
Let me ask another question.
I just can't understand what you said.
Can you embed coloring problems in these CSH problems?
Embed what problems?
Coloring problems. You want to color, how
Yeah,
many
these
colors there should be particular cases, and then there are non-commutative coloring problems. Does that work as well?
No, these are all coloring problems.
They are non-commutative coloring problems.
Non-commutative. Oh.
Yeah. And that they should also have a Hamiltonian, and so
Yeah, no,
they should very naturally fit into this picture.
definitely, there's like a million things. So we don't know the basics about this, very basic, MaxCut and MaxKcut are the first CSPs you're going to look at in CS. There are a million more complicated CSPs that I have looked at and other people have looked at. But I feel like for me, I haven't even bothered looking at what other models quantumly we can do, because it's so hard already to understand these toy. I'm going to call them toy, but they're not easy, so I feel like as long as I understand this first, then there's going to be room.
Okay, so what I suggest is maybe to understand something else first.
Okay.
For instance, there's this incredible good work of Hastings about quantum expanders.
Uh-huh.
And if you use these kind of very good techniques, you can maybe understand these problems. I don't know, right? But it makes sense to ask for, to use some other big tools and see whether
What are
there you can.
quantum expanders?
Quantum expanders are exactly the analog of
Oh, you mean the quantum graphs, like, or,
it's just unitaries which have a uniformal spectral gap.
okay.
UI bar with a uniformal spectral gap.
'Cause
So
there's
they're
this
very
thing that's
natural.
called quantum graphs. That's something completely different that I'm also
No, it's
working
very
on.
closely related, but
Yeah,
not
yeah, okay.
exactly the same. Yeah, so there are many similar models, but there we have more quantum information about quantumness, right?
Yeah, okay. No, that's actually a good idea. Yeah, thanks. I'm new to this, my students, are suggesting.
Okay, any further questions? All right, that doesn't seem to be the case, so let's thank Alexandra again.